Displacement ventilation is a relatively new concept in North America that combines innovative technology with natural forces to distribute air in a space. In this unit, we'll explore the concept behind displacement ventilation, its benefits, and how it compares to other air distribution systems. Once we understand that, we'll look at Price's displacement diffusers, which are varied in shape and size to cover a wide range of applications. We'll learn the importance of properly configuring a room in order to achieve superior air quality and deliver large volumes of air in an efficient way. Displacement ventilation uses an innovative technology based on three major principles: supply air, buoyancy forces, and stratification. First, supply air enters directly into the occupied zone at a low velocity. Its temperature is slightly cooler in order to displace the warmer, polluted air already present in the room. Objects commonly found in the room, such as people, computers, and lights, give off heat that provide buoyancy forces. Each of these heat sources warms the surrounding air, and this warm air rises up away from the heat source. These convection currents, also known as thermal plumes, are responsible for the circulation of air in a displacement ventilation system. The warm, contaminated air is lifted out of the breathing area, allowing clean air pooled near the floor to take its place. Depending on the power and geometry of these heat sources, the plumes could rise all the way to the ceiling. This means that the returns should be positioned where the highest temperatures occur, which in most cases is the upper part of the room. This is where stratification comes into play. Air in a room divides itself based on temperature. The hotter air rises while cooler air falls. By introducing cool air at lower velocities than a normal mixing system, we're able to flood the lower levels with clean, cool air, thereby pushing the polluted warmer air higher than the occupied zone to be drawn out by high-level returns. Now that you understand the basics of how displacement ventilation works, let's see how it compares to the more conventional mixing system. To determine whether displacement ventilation or mixing ventilation is better suited for each situation, we must understand the differences between them. A conventional mixing system usually introduces cool supply air at high velocities at or near ceiling level. The high outlet velocity causes induction of room air, thereby rapidly mixing the supply air with the room air. This mixing effect minimizes stratification in the room. Typically, supply air temperatures of 55 to 60 degrees Fahrenheit are selected for a mixing system. In a displacement ventilation system, the air is introduced at the floor level, and there is minimal mixing with the room air. Because the supply air is directly introduced into the occupied zone, it cannot be as fast or as cold as in a conventional mixing system. Typically, supply air temperatures of 65 to 70 degrees Fahrenheit are selected for a displacement ventilation system. In most cases, the returns are in the upper part of the room. We'll examine more of these differences in the following benefits section. Benefits. Displacement ventilation offers many benefits. It can improve indoor air quality, increase ventilation effectiveness, save energy and cost, and help qualify for LEED certification. In a displacement ventilation system, since the air is not distributed uniformly like it does in a mixing system, contaminants such as CO2, fumes, humidity, and smoke rise and are removed from the occupied zone. This greatly improves the indoor air quality, or IAQ. In fact, by considering the requirements published by the American Society of Heating, Refrigerating, and Air Conditioning Engineers, also known as ASHRAE, Price's family of displacement ventilation products are designed to be energy efficient, cost-effective, and promote a clean, healthy environment. Ventilation effectiveness can be defined as how effectively airborne contaminants are removed from a room. It can be determined by comparing the level of contaminants in the occupied zone to the contaminants in the exhaust leaving the room. Basically, if there are more contaminants in the return and less in the room, you have a high level of ventilation effectiveness. If the concentration of contaminants at the return is equal to the concentration of contaminants in the occupied zone, the ventilation effectiveness equals 1. If the concentration of contaminants at the return is greater than the concentration of contaminants in the occupied zone, the ventilation effectiveness is greater than 1. Ventilation effectiveness in a mixing system is typically measured at about 0.8. Displacement ventilation is typically measured between 1.2 and 1.4, providing superior indoor air quality by removing contaminants and supplying clean air more effectively. A benefit of displacement ventilation is its low energy consumption. 3 ways that you can save energy with this system are in fan speed and size, chiller efficiency, and free cooling. Used properly, it can be a cost-effective alternative for handling any building's cooling requirement. In a mixing system, air is introduced into a space at cool temperatures and high velocities. The room air is then mixed equally throughout the entire space. For buildings with high ceilings such as factories or gymnasiums, the energy needed to adequately cool a space is extensive. On the other hand, displacement ventilation only delivers fresh air to the lower areas of the room where it's needed. As a result, there are smaller volume requirements placed on the system. In addition to this, the lower pressure and velocity of the supply air coupled with the reduced fan power greatly decrease energy consumption. Just as the supply air temperatures are higher in a displacement ventilation system, so too are the return temperatures. In a typical mixing system, the supply air temperature is approximately 55 degrees Fahrenheit and the return air temperature is approximately 75 degrees Fahrenheit. In a displacement ventilation system, the supply air temperature is approximately 65 degrees Fahrenheit and the return air temperature is approximately 80 degrees Fahrenheit. The higher return air temperature is beneficial because it allows our chiller to work with a higher coefficient of performance, saving us energy and money. The third point of energy conservation is free cooling. This refers to the concept of using outdoor air for cooling indoor environments. In regions where humidity does not present a problem, and when outdoor temperature is lower than the supply temperature, the system can turn off the chiller and switch to using outside air for cooling. Since displacement systems have a higher supply air temperature, longer periods of free cooling are available throughout the year. Naturally, these benefits will vary depending on your location and climate. All of these benefits can be accumulated towards achieving LEED recognition. LEED stands for Leadership in Energy and Environmental Design and is a national standard defined by the U.S. Green Building Council. The program is based on these primary categories: innovation and design process, sustainable sites, water efficiency, energy and atmosphere, indoor environmental quality, and materials and resources. Points or credits are rewarded for various items in each of these categories. Buildings are deemed LEED buildings if they earn a certain number of points. Displacement ventilation qualifies for LEED points in several areas. Under the category of indoor environmental quality, displacement ventilation provides ventilation effectiveness, low discharge velocities, and supply air temperatures which exceed LEED requirements, earning possible credits. Under the category of optimized energy performance, more points are available for the energy-reducing benefits that displacement ventilation provides. The extremely low noise level of displacement diffusers can be applied towards a credit for exceptional acoustic performance in the Innovation in Design category. To summarize, displacement ventilation qualifies for the following LEED requirements: ventilation effectiveness, thermal comfort, optimized energy performance, and innovation in design. Considerations. As you can see, displacement ventilation offers many advantages. However, there are a few points that you should consider as well. While it is exceptionally efficient in cooling situations, displacement ventilation alone cannot effectively be used in heating solutions. Heated air introduced by the diffuser tends to rise and reach the returns before they get a chance to enter the occupied space, thereby short-circuiting the system. In environments where both heating and cooling are needed, the displacement ventilation system should be supplemented with options such as baseboard radiation, ceiling panels, or fan coil units. Due to the higher temperatures in use, humidity may be a concern with displacement ventilation. The displacement ventilation system has a supply air temperature of approximately 65 degrees Fahrenheit as opposed to 55 degrees Fahrenheit found in conventional mixing systems. At this temperature, less moisture would be extracted at the cooling coil, and humidity could rise to unsuitable levels. In order to achieve proper dehumidification in a displacement ventilation system, we might still cool the circulated air to 55 degrees Fahrenheit, then reheat it to the desired air temperature of 65 degrees Fahrenheit before introducing it into the environment. This can be accomplished in several ways. Most commonly by mixing the warm filtered return air with the conditioned air at the air handler or at the terminal unit. In some cases, a heat exchanger might be used to transfer heat from the return air stream, or in rare cases, a heating coil may be employed. Displacement diffusers must be selected and located carefully to avoid drafts. Generally, occupants should be seated no closer than 2 feet from the diffuser face. A maximum of 40 feet per minute face velocity should be maintained when sizing the diffuser. A simple way to minimize the effect of drafts is to provide a greater total face area. This means using either bigger diffusers or more of them. By installing more diffusers, the airflow is divided among a greater number of locations and the velocity at each of the diffusers can be decreased. By choosing diffusers with particular airflow patterns, you can carefully position a few bigger ones in unoccupied regions of the room. So where can we use displacement ventilation? Displacement ventilation is usually a good choice in the following cases where air quality is a major consideration, the contaminants are warmer or lighter than the room air, the supply air is colder than the room air, the room heights are 9 feet or more, or low noise levels are desired. Displacement diffusers. This section provides a basic overview of diffusers, the different types available, and where to set them up in a room. A wide variety of displacement air diffuser types are available to suit any location needs: rectangular, corner, semicircular, circular, floor-mounted, and custom-built. A wide variety of displacement air diffuser types are available to suit any location needs. We'll look at some common types. Rectangular units are typically placed against a wall or partition. If only the face of the unit is active, a one-way pattern is produced. If both the face and sides are active, a three-way pattern results, with a higher volume capacity. Diffuser inlets are usually at the top of the unit, although bottom or rear inlets are available. Corner units are designed to fit into a 90-degree corner in a room. Supply inlets can be located at the top or bottom of the unit. Flat or semicircular faces are available depending on the desired look. A 90-degree radial pattern is produced by corner units. Semicircular units are typically placed against a wall or pillar. Supply inlets can be located at the top, bottom, or rear of the unit. A 180-degree radial pattern is produced. Circular units can provide high volumes of air to a space because the air is distributed in a complete 360-degree radial pattern. The supply inlet can be located at the top or bottom of the unit. They are usually placed freestanding in large interior spaces such as halls, lobbies, and lounges. Displacement diffusers are available for integration with a raised floor distribution system. The round floor displacement unit produces a low-velocity radial pattern across the floor. Displacement diffusers can be mounted in numerous locations and configurations. Following are some general recommendations for supply diffusers. Rectangular or semicircular units are often located on walls opposite to the exterior windows and walls. For large rooms wider than 30 feet, consider mounting the diffusers on 2 opposite walls. For rooms longer than 15 feet, consider several diffusers along the wall as opposed to one. For large open spaces, diffusers can be placed in the middle of the space. Place more diffusers in areas which have a higher cooling load. Avoid placing large obstacles near the diffuser face. Place diffusers no closer than 2 feet from the occupants. For the air return outlets, it's essential that they be placed at high levels, either on the wall or in the ceiling. The same model types for mixing systems would apply to displacement systems. Locating the return air outlets above strong heat sources will ensure the efficient removal of the heat and contaminants generated by the thermal plume. Design considerations. For all displacement ventilation systems, the load calculations are quite different than they are for traditional mixing systems. The cooling load of a room or a space is determined by the heat sources present, such as lights, occupants, equipment, and solar gain. Because a mixing system cools the entire volume of the space, we must account for all of the heat sources in our calculation. With displacement ventilation, we're only concerned about the occupied zone, or the lower 6 feet of the room. Heat sources both inside and outside of this space contribute a portion of their heat to the occupied zone and to the upper zone. Heat sources transmit energy to the space through both convection and radiation. The portion of a heat source which is convective or radiant will vary by the type of heat source. This table illustrates the portion of convective and radiant load for several common heat sources. In a displacement system, the convective portion of the load rises naturally and is exhausted at the ceiling without contributing to the load in the occupied space. The radiant portion of the load will be distributed between the upper and occupied zone, depending on the location of the heat source. Let's examine the lighting in the space and see how the lighting load is divided between the two zones. It's easy to see how overhead lights contribute the majority of their load to the upper zone. A light fixture has a thermal plume, but because it's already in the upper zone, all of the convective loads will be in the upper zone. The radiative component of the lighting load will put a smaller load in the occupied zone as heat is transferred to all surfaces in this space. Solar loads are slightly more complex. When no shading is used, the majority of the solar load falls on the floor, which is in the occupied zone. As the floor heats up, it passes some of its heat to the surrounding air, causing a portion of the load to enter the occupied zone. The warm floor also radiates some of its load to other surfaces in the space, including room walls and ceilings, which are outside of the occupied zone. If a shading system such as blinds is used, the sun heats up these vertical surfaces instead of the floor, creating a thermal plume along the perimeter. These plumes carry the heat into the upper zone without entering the occupied zone, further reducing the amount of heat gained in the occupied zone due to the sun. We know that task lighting, equipment, and occupants located in the occupied zone have thermal plumes. These naturally exhaust a portion of their heat to the upper zone, even without cool supply air. As a result, a portion of their convective load is passed to the upper zone, while some of it remains in the occupied zone. These surfaces also radiate heat to other surfaces, but for the same reasons as with the solar load, some of this may be outside of the occupied zone. Since only a portion of the load from the heat sources affects the occupied zone, we can adjust our calculation when determining the total room load. Calculation of the room load may require the use of energy analysis software and may vary in each application. A recent publication from ASHRAE System Performance Evaluation and Design Guidelines for Displacement Ventilation proposes a methodology for calculating cooling loads, supply air volume, and supply air temperature of a displacement ventilation system. Refer to our design guide in the displacement ventilation section of our catalog for a detailed explanation of this procedure. It should be noted that the ASHRAE publication is based on research conducted on offices, classrooms, and industrial workshops. It should not be applied to large spaces such as theaters or atria. Conclusion. We hope that you've enjoyed this look at displacement ventilation. As we've seen, displacement ventilation is an innovative new approach to air distribution that has many benefits and should be considered when configuring your HVAC system. For more in-depth information on what's covered in this training module, you can always refer to the Price catalog. Be sure to explore the other units in this price training module to learn more about air distribution as well as the extensive line of price products available.